through SRC-related kinases that activates the phospholipase C pathway. A critical factor for phagocytosis is the activation of the GTPase dynanim, which contributes to vesicle internalization in multiple ways, including the pinching off of the neck of the internalized vesicle, a molecular garrote, if you like. However, which signaling elements are important for phagocytosis has been somewhat controversial, and the pathway for the activation of dynanim is unknown. It has long been known that one of the earliest events that accompanies phagocytosis is an increase in calcium. But as this recent review points out, there has been some disagreement as to whether the calcium signal is actually required for driving phagocytosis. This table lists examples in the literature where calcium has been shown to be important or not. Green says, yes, it is important, and red says no. And you can see that there isn't really a consensus. In view of this, we decided to revisit this issue and see if we could shed any light on this confusion. Therefore, we set out to determine if phagocytosis was calcium dependent, which calcium source, and whether the spatial calcium pattern is important. We used mouse macrophages, either primary cells from various mouse lines, or for transfection studies, the raw cell line. The experiments I'm going to show you today quantify phagocytosis from the uptake of fluorescent beads and calcium measurements using confocal microscopy. Throughout the talk, I will present calcium recordings under various conditions, and then the equivalent bead uptake experiments in parallel. So we dropped IgG-coated beads onto macrophages loaded with a cytosolic calcium dye, and the rapid calcium responses to FCR activation were comprised of two phases, as expected, an initial increase followed by a more sustained phase. In the absence of extracellular calcium, only the initial release from intracellular stores is observed. Finally, this calcium release from stores was entirely suppressed by loading the cytosol with Bapta. But what are the effects of these manipulations on bead uptake? Compared to the control, the removal of extracellular calcium shows no change at all in phagocytosis. This clearly indicates that calcium influx plays no role in driving phagocytosis. In contrast, suppressing the calcium rise with Bapta severely inhibits bead uptake, whereas a control Bapta analog that poorly binds calcium does not inhibit. So these data show that it is the release from intracellular stores and not influx that drives phagocytosis. So the Bapta data suggested that calcium is important, so we began to assess which sources. First, is global calcium important? In macrophages, the substantial global calcium response is driven by both IP3-dependent release from the ER as well as store-operated calcium entry. We removed extracellular calcium to eliminate influx, and we eliminated the residual calcium release phase in two ways. Either we pre-depleted the ER with SERCA inhibitors, thapsogardin or CPA, or we loaded the cytosol with the slow calcium chelator EGTA and monitored the impact on calcium signals and phagocytosis. So in calcium-free medium, FCR engagement evokes global calcium oscillations in control cells. However, when the ER was depleted with either CPA or thapsogardin, these responses were all but eliminated. In a similar way, loading the cytosol with EGTA also inhibited the global calcium signals. Remarkably, eliminating these calcium responses failed to have any effect upon bead uptake. That is, the global calcium responses are not required for phagocytosis. At first glance, these data do not seem to agree with the calcium dependence suggested by cytosolic Bapta. However, the discrepancy can be resolved because Bapta is a fast chelator that collapses local calcium domains, whereas slow EGTA cannot. In other words, With EGTA or SERCA inhibition, are there invisible local calcium signals that persist and continue to drive phagocytosis in a calcium-dependent manner? So we therefore considered other sources of calcium that are not in flux or the ER and asked if lysosomal calcium signals drive phagocytosis. It's worth emphasizing that lysosomes on their own cannot generate large global calcium signals and are best suited to local calcium signaling. Given that the luminal free calcium concentration in the lysosome and the ER is about the same, then the total amount of releasable calcium will be proportional to the physical size of the store. In a typical cell, the volume of the ER is far larger than the total lysosome volume. Consequently, the lysosomes release a small total amount of calcium compared with the ER. And in this cartoon, I've actually exaggerated the contribution of the lysosome store, which in many cell types is so small that it's invisible in global recordings. But we hypothesize that it is this small component that is key to phagocytosis. In this simplified cartoon of a lysosome, the lumen is acidic because of the proton pump, and the route of calcium uptake is controversial. But one model is that the acidic lumen drives calcium uptake via some form of calcium proton exchange. On the calcium release side, several families of calcium permeable channels are proposed, and I'm only showing two here, the 2-pore channels and mucolipins, TRPML1. The regulation of these channels is complex and physiologically unclear, but for simplicity, we consider that calcium release from TPCs is stimulated by the second messenger NAADP, whereas TRPML is updated by the lysosomal lipid PIP2. So first, we investigated whether lysosomes are important for phagocytosis by interventions designed to lower the luminal calcium concentration and thereby calcium release. Because there's no lysosomal thapsigargin, we used other strategies. One common approach is to inhibit the proton pump with baphlomycin to reduce the driving force for calcium uptake. We also chelated the luminal calcium by trafficking extracellular chelators to the lysosome via endocytosis. In this case, we used dextran conjugated versions. So in calcium-free medium, beads evoked global calcium signals, and these were only modestly reduced by pretreatment with baphlomycin. We also pre-incubated cells with different dextrans, those that bind calcium and those that do not, and trafficked them to the lysosome lumen. And regardless of the calcium binding characteristics, dextran loading also had only a minimal effect upon the global calcium signals. But turning to the all-important bead uptake, these conditions predicted to lower the lysosome calcium levels, baphlomycin and the calcium binding dextran severely inhibited the phagocytosis of beads compared to the control. In contrast, the non-calcium binding dextran controls did not alter uptake. This was our first hint that lysosomal calcium signaling is important for phagocytosis. In view of the potential roles of lysosomes, we investigated which channels might be involved, focusing on TPCs and mucolipins using pharmacological and genetic approaches. Our main focus was TPCs. We first asked if the NAADP-TPC pathway operated in mouse macrophages. Because NAADP is a polar messenger, we increase cytosolic NAADP by incubating cells with a membrane-permeant AM ester, a prodrug version. In control cells, NAADP-AM evokes calcium oscillations, and importantly, these are blocked by the NAADP antagonist, NED19, inhibition of the lysosomal calcium storage with baphlomycin, or by eliminating the NAADP target channel TPC2 in macrophages from knockout mice. This shows that the NAADP TPC axis operates in macrophages, but the next step is to ask whether it's important for phagocytosis. Therefore, we asked whether FCR-evoked calcium signals require lysosomal channels. So first, NED19 lowered the phagocytic calcium signal, consistent with NEADP playing a role. Similar to the effect of NED19, eliminating the NEADP targets, TPC1, TPC2, reduced the calcium signal. In contrast, knockout of TRPML1, which is not activated by NEADP, has a much smaller impact on phagocytic calcium signals. Together, this data indicates that NEADP and its target channels, TPCs, are important for phagocytic calcium signals, whereas NEADP-independent TRPML1 channels are not. Turning to the bead phagocytosis, the reduced calcium signals were mirrored by reduced bead uptake. Compared to wild-type control, the knockout of TPC1 and TPC2 substantially inhibited bead uptake. Again, the other lysosomal channel, TRPML1, appeared to play no role since its deletion had no effect on bead uptake. To confirm that the inhibition of uptake was specifically due to the loss of TPC channel, we rescued the response by re-expressing the missing isoform. Moreover, this rescue required that an active channel be expressed because a poor dead mutant channel failed to rescue. As with calcium then, active TPCs, but not TRPML1, are key for the FCR-mediated phagocytosis. As a mini summary, we show that FCR-mediated phagocytosis does not require either calcium influx or calcium release from the ER. That is, global calcium is not a driver of phagocytosis. Instead, it's the lysosomal calcium stores that are important. But interestingly, not all lysosomal calcium channels take part. TPCs are key, whereas TRPML1 is not. But we'll return to this specialization a bit later. So having shown that the global calcium signals are dispensable, could we show that the local lysosomal calcium signals drive phagocytosis? So recall that one piece of evidence supporting a role for local calcium signal were the differential effects of the cytosolic BAPTA and EGTA. So fast BAPTA collapses local domains, whereas slow EGTA cannot. However, this does not tell us where these domains are generated. So we gained evidence for their existence and their importance. And for this, we needed lysosome-specific strategies. Therefore, we used complementary approaches of monitoring and manipulating lysosomal calcium nanodomains. So to selectively buffer calcium at the lysosomal surface, we use the well-known drug-induced dimerization strategy that brings two proteins together upon addition of rapalog. By targeting one half to the lysosomes, we could translocate tandem copies of the calcium-binding protein calbinding 2 to the vesicle surface, i.e. 10 calcium-binding sites per molecule. And we used non-calcium binding versions as controls. So the graph shows the Pearson's correlation coefficient between the different constructs and lysosomes. For all constructs, addition of rapalog brings the proteins to the lysosomes, as indicated by the increased coefficient compared to the ethanol controls. And this is also reflected in the yellow overlap between the protein and the lysosomes in the images. But crucially, bringing the calcium buffer to the lysosome with rapalog inhibited bead uptake when compared to the non-translocated ethanol control. And this inhibition correlated with the ability to bind calcium because neither the triple BFP nor the mutant calbindin affected bead uptake. Therefore, targeting calcium buffers to the lysosome supports our model that local lysosomal signals drive phagocytosis. So I've shown you we can manipulate the lysosomal calcium domains, but can we also monitor them? Because lysosomal calcium domains are invisible in global recordings, we fused genetically encoded calcium indicators, GECIs, to the channels themselves to see if we could detect locally high domains immediately around them. To match the Gecki KD to the micromolar range of the nanodomain, we used the low affinity GGECO 1.2, which I'm going to refer to from now on as GG. So FCR stimulation evoked robust TPC2 GG spiking, confirming that calcium is indeed elevated around TPC2. However, it doesn't tell us where the calcium comes from, and this required additional controls. First, the Gecki could simply be picking up global cytosolic calcium signals. So to assess this, we also used the unfused cytosolic GG, and it could indeed detect phagocytic calcium oscillations. However, the TPC2 GG responses were significantly larger than the cytosolic GG signals, consistent with TPC2 GG detecting domains that the cytosolic form could not. And importantly, this larger signal was not just dependent on the lysosomal location, but on the channel being active. Because when we inhibited the TPC activation in two ways, using the NADP antagonist NED19, this reduced the response to cytosolic GG alone. And secondly, expressing a poor dead inactive mutant also eliminated the local component. Therefore, TPC2 GG detects calcium signals that cytosolic GG cannot, and this is dependent on an active channel on the lysosome. Earlier, I showed you that eliminating the global calcium response had no impact on bead uptake. And if our hypothesis is correct, then under these conditions, the local lysosomal calcium signals should still remain. So using the TPC2 GG, we tested this. And in these recordings, we've simultaneously recorded the global calcium responses using a calcium dye that's shown in grey. And all experiments are in calcium-free media. So in control cells, beads evoked calcium spikes in both the global and local signals. And at the end of the run, we applied ionomycin and calcium to swamp the cell as a positive control. Crucially, the local TPC2 GG response remained even when the global signal was eliminated by pre-depleting the ER with thapsigargin or CPA. In a similar way, the local TPC2 GG response persisted in cells loaded with cytosolic EGTA, which suppressed the global signal. So in summary, we've shown that local lysosomal calcium domains can be blocked by lysosome-targeted calcium buffers, are only detected with channel Gecki fusions, are independent of global calcium, and I've not got time to show you all the data, but we've also shown that local TPC2 GG signals were stimulus-specific, so they're acting via the FCR, but not by an IP3-linked GPCR. So at the start of the talk, if you remember back then, I told you that dynanin was important for uptake, but that its mechanism of activation was unclear. And I haven't got time to show you all the data, but we recently suggested that these TPC domains drive dynanin activation. So dynanin can be activated by dephosphorylation, and we show that this is a TPC-dependent activation, probably via acute activation of the protein phosphatase calcineurin. And this provides a complete pathway to dynanin activation. So in the final section, I'll touch upon another aspect that different lysosomal channels do different tasks at phagocytosis. So what I didn't tell you earlier is that different processes are recruited to phagocytose particles of different sizes. So dynanin-induced scission is a universal requirement for all particle sizes. In contrast, to completely envelop large particles, additional membrane is required, and this is provided by the exocytosis and fusion of lysosomes with the plasma membrane. Note that the doubling in bead diameter equates to an 8-fold increase in volume. So in short, small particles require dynanin activation, whereas big particles require dynanin plus extramembrane via exocytosis. But how are these discrete requirements regulated? So in the following experiments, I will compare small and large beads and the pathways recruited. So the data I previously showed you corresponded to 3 micron beads, which I'm calling small, where bead uptake was severely inhibited in TPC1 and TPC2 knockout cells. And this dependence on TPCs also holds for larger beads, 6 micron beads, as uptake is also reduced in the knockout cells. In contrast, TRPML1 knockout has no effect whatsoever on the uptake of small beads, but it does inhibit the uptake of large beads. So there's a size discrimination for TRPML1. This begs the question of why the differential reliance. And one possibility could be that these channels are differentially activated by different stimuli. So we therefore used our channel Gecki approach to monitor each channel's activation with different size beads as stimuli. So we saw that TPC2 channels were activated by both small and large beads, since the amplitudes were greater than the cytosolic GG, shown by the dotted line. So the previous slide shows that both bead sizes required TPC2 for uptake, and this calcium activation pattern mirrors that. On the other hand, the activation of TRPML1 was stimulus dependent. Only large beads activated the channel. So this correlated perfectly with the fact that the uptake of small beads did not require TRPML1, whereas large particles did. So in a nutshell, the macrophage doesn't activate a channel family unless it needs it. So expanding this scheme, dynanim is universally needed by particles of all sizes to internalize the phagosome, and TPCs drive this pathway. So, but only when emergency membrane supplies are required will lysosomes exocytose and fuse with the plasma membrane. Therefore, the TRPML1 pathway is only activated and required for these bigger particles. This is why bigger particles exhibit a dual dependency on different lysosomal channel families. How this exquisite compartmentation at the level of the lysosome is established architecturally is unclear. So our working hypothesis is that calcium sensing decoding molecules like calcineurin and synaptotagmin 7 physically associate with their respective upstream channel and only sense the locally high calcium nanodomain in its immediate vicinity. This would conveniently explain why the channels cannot substitute for each other. So, for example, in our recently published paper, we showed that the stimulation of TRPML1 cannot rescue the TPC knockout phagocytic defect. So in summary, we propose a model where different lysosomal calcium channels coupled to different downstream pathways via their exquisite calcium nanodomains. And finally, I'd just like to thank Anthony Gaglione in his lab, Anthony Morgan, Guy de Ruras, and the Wellcome for funding. And